So thank you for letting me speak. I think what I'm going to try to do today is less about my research and more about polynomials, hyperbolic polynomials, and real stable polynomials as a tool that's particularly useful for certain situations, and also sort of talk about hyperbolic programming, which is something that could be of interest to you guys in computer science. So let me start with real-rooted polynomials. So univariate, real-rooted polynomials. And let me make two observations. First is that if P is real-rooted, just write RR, then P prime is real-rooted. Right, this comes from Rolle's theorem. In between any two roots, you have to have a derivative equal to 0. And secondly, if P of x is real-rooted, then x to the n P of 1 over x is real-rooted. This essentially just takes the coefficients and flips them backwards. And what it does to the roots is it makes them 1 over the roots, right? Assuming that, let's say, there are no zero roots. And this seems like not all that exciting, but already we can use these to derive something that's fairly non-trivial, which are called Newton's inequalities. And Newton's inequalities say that if P of x is a0 plus a1x plus ad x to the d. So a polynomial of degree d, which is real-rooted.
So real-rooted, you mean all the roots are?
All the roots are real. There's x minus, product of x minus real numbers. If this polynomial is real-rooted, then you have that, so ai over d choose I squared is greater than or equal to ai minus 1, ai plus 1, d choose I minus 1, d choose I plus 1. These are Newton's inequalities. And they are fairly easy to prove. So why don't I do it right now? So you can prove this by induction. The case when d equals 2 comes down to, so that means I have a2x squared plus a1x plus a0. So this is just saying that a1 squared over d choose 1, which will be 4, is greater than or equal to a0 over 1 times a2 over 1. And this comes directly from the quadratic equation. So this is quadratic equation. And now for more general d, you can prove d plus the discriminant being non-negative. For general d, what you can show is that anytime you take the derivative, you go from these quantities d plus 1 choose I will go to this quantity d choose I. So for all of the inequalities except for the very first one, you get that from by induction. And then to get the first one, you just need to reverse the polynomial and then take the derivative, and then that will give you.
So you really need the property.
You really need the reversing property, yeah.
So in some sense, it's better to write real rooted polynomials with this normalization.
Yeah, sometimes, yeah.
Convexity or
So yeah, so this is called ultra-log concavity. And the fact that this is actually very important, and it's kind of a pain because it sort of shows you that being very close to real rooted doesn't necessarily help you all that much, because when you take 1 over x, that shoots these roots to who knows where. And so one of sort of the downsides of dealing with real rooted polynomials is that it's a very 0-1 sort of situation. Like either you have a real rooted polynomial, in which case you're very happy, or you don't have a real rooted polynomial, in which you need to do something else. But I should mention that this inequality here appears in other places. So in convex geometry, for example, there is what is known as a Steiner polynomial. And a Steiner polynomial is sort of the convex geometry equivalent of a characteristic polynomial of a matrix, right? So for a characteristic polynomial, we have determinant of xi minus a. For convex geometry, the identity is essentially the unit ball, and you're asking about what is the volume of epsilon times the ball minus whatever your, this is some convex body. Now it turns out that this is a log concave polynomial. In fact, all log concave polynomials are defined by some convex body, so they're isomorphic to each other.
This is a polynomial in epsilon.
This is a polynomial in epsilon. It doesn't really, yeah. And it satisfies A choose I over D choose I squared is greater than or equal to AI plus 1. But it is not necessarily real-rooted, and in fact, the sort of an arbitrary one will not be real-rooted. So, so this reverse implication is not true. But the fact that this is true is a result due to Alexandrov and Fenchel. And it is extremely non-trivial. Much, much, much more non-trivial than what we did. So this sort of gives you an idea of, why would you want to even bother dealing with real-rooted polynomials? And the answer is, if the thing that you're dealing with really doesn't need all of the power that comes with Alexandrov-Fenchel or these convex geometry sorts of inequalities, then you're very much better off turning it into a real-rooted polynomial if you can do that. So in fact, I'll talk about the lower bound on the permanent. The original proof of the lower bound on the permanent used the Alexandrov-Fenchel inequalities and won the Fulkerson Prize, and was also sort of used them in a non-trivial way. And using polynomials, we can do the same thing in like maybe a line and a half. So here's our first sort of indication that, that these things might be interesting. Let me give you another inequality. This is an inequality due to Gervitz. And it says that if P of x is the sum for AI x to the I, is real rooted with all of the AIs greater than or equal to 0, then and C is the infimum over t greater than 0 of f of t over t. Then this implies f prime of 0 is greater than or equal to c times n minus 1 over n to the n minus 1. This should be degree n. Yes, sorry. Thank you.
What should we understand? This inequality, what does it really say?
So it's somehow telling you that you can make comparisons about derivatives if you understand, what this f of t over t is.
So that's what I mean, the definition of C.
So it's not going to be obvious now, but it will be obvious when we use it for real stable polynomials. So this is going to turn into, when you have a multivariate polynomial, this will turn into the capacity.
Yeah.
And the proof, again, is not particularly hard. So what this says is that Ct is less than or equal to f of t for all t. And using AMGM, you can show that this is less than or equal to 1 plus a n minus 1 over n a n to the n. AMGM, so I'm writing it as,
Inside the polynomial in T and then.
sorry, there's a t here. Yeah, write the polynomial in T. This is always positive on the positive real numbers. So you replace t minus a with so instead of product over I, t minus ri, you replace that with sum over I, t minus ri over n to the 1 over n.
To the n.
To the n. Yeah. And then this becomes something that looks like this, and then you can do calculus to find the t, which is the sort of optimal t for this. And it's kind of a pain to do, but it ends up giving you this n minus 1 over n to the n minus 1. So not particularly hard. Any questions so far? Okay. So one thing I wanted to mention is the idea. So one of the important ideas in real-rooted polynomials is the idea of interlacing. So given polynomials, real-rooted polynomials, P and Q, where P is I may have written it. You probably have to do it like this. Write it like this, probably. Is that what you were asking about?
Yeah, you have to take the reversal, right? It's not f anymore, right? This is the reversal. write it that way?
Yes, it'll be the reversal. So you can write f as the reversal of f. So these are, sorry. So you would have to write, you can always write f of x as pi over I 1, say, minus tri over n for some ri's. Not the roots of f, but the roots of the reversal of f. And then when you add them up, you end up getting this. And sorry. So we say that P and Q are interlacing if, for instance, R1 less than or equal to Q1 less than or equal to R2. And less than or equal to Qn. Or maybe Rn has more roots than Q does, in which case that's fine as well.
I mean, S size, but
Sorry, yes, S. So for example, P prime of x interlaces P of x. For exactly the same reason as before, in between any two roots of P, you have a root of P prime. And the reason that interlacing is important is because it gives a structure to the collection of real-rooted polynomials. It gives it some sort of ordering. And in particular, you can show that there are an equivalent definition of, so P and Q interlace if and only if alpha P plus beta Q is real rooted for all alpha and beta. And so P and Q have a common interlacer. So that's some other polynomial that interlaces both of them if and only if alpha P plus beta Q is real rooted for all alpha and beta greater than or equal to 0. So this idea of interlacing is sort of intimately connected to real rootedness and will end up being something that we'll use to prove a lot of things. Any questions so far? Good. So then you might think, well, okay, real-rooted polynomials are very nice. How do I go about showing that something is real-rooted? I mean, that's sort of, if it came along and said, like, I'm real-rooted, that, would be very nice, but typically that's not going to be the case. And it turns out that in order to sort of really understand the way that you can prove things to be real-rooted, it helps to move to multivariate polynomials. So let me define H to be the upper half plane, such that imaginary. And I will say a multivariate polynomial P of x1, xn is stable if P has no roots in H to the n. So if you plug in a bunch of values that have positive imaginary value, your polynomial is not 0. Now, to see that this is an extension of real rootedness, when p is a univariate polynomial, remember that, so I should call this real stable. Stable plus real coefficients. So real stability is actually a generalization of real rootedness, because if you have a univariate polynomial that has real coefficients and is not real rooted, then it has 2 roots, but the roots come in conjugate pairs. So in particular, you must have, if it has complex roots, it has to have a root in the upper half plane. And so this is the sort of the way that we can generalize the idea of real rootedness. And the picture that I like to use to remember is sort of something like this. So real stable polynomials, this tends to be what their 0 sets look like. And this is sort of the positive orthant. So this contains the positive orthant. This is in, let's say, 2-dimensional bivariate. A bivariate, so it's a p of x and y.
Over the complex numbers?
Over
the Euclidean plane or the complex?
Over the Euclidean plane.
Okay.
Yeah. And so,
It's a picture of R4, I guess.
no, this is R2.
Because you take the imaginary as
So this is a plot of R2, and these are where this function is 0 when you plug in those points. And the general idea is that
think of x as line as real.
as real, yeah. So the general idea is that you have this lobe over here, and we'll see this lobe again. Maybe I should have done that first. Okay. But the point of real stable polynomials is that you can use them to sort of generate real rooted polynomials.
Why
Yeah.
is the orthant sitting there? It's not, the real stable.
Oh yeah, if this has positive coefficients, I'm sorry. Positive coefficients. If it doesn't have positive coefficients, it could be shifted, sort of. This will make more sense in about a minute. So the reason that these multivariate polynomials, the real stable polynomials, tend to be useful is that they have lots of nice closure properties. So so just like in the univariate case, p of x1, xn, real stable, implies real stable. Yeah.
I completely didn't understand the picture. Can you explain what it demonstrates?
So, like for instance, xy equals 1, for example, right?
So does it demonstrate a real stable polynomial or something which is not real stable?
So it's real stable, but it's not. It doesn't have the positive orthant in here. I mean, not. So xy equals 1
Your polynomial is something equals to 0, right?
Yeah, so, all right, so let me not do positive coefficients, and let me just do this. So xy minus 1 will be this. And in general, a a real stable polynomial will look like this on the ends, and will have sort of 0 sits in the middle. And so the idea of why this partial derivative is the partial derivative maintains real stability is that if you look at some line that goes like this is a real rooted polynomial. And so when you take derivatives, it's sort of the 0 sets of the derivative sort of fall in between these sort of lobes, I guess. So secondly, P of x1, xn real stable implies 1 over xi I need a minus there. So you can do inversion. And last but not least, if P of x1, xn is real stable, then P of x1 t is real stable for all t with imaginary part of t greater than or equal to 0.
X n minus 1 and t.
N minus 1, yeah. So I'm just plugging in some.
So you fix a constant at some coordinate, and so you go down dimension.
You go down a dimension, you fix a coordinate. And for imaginary part of t greater than 0, it's trivial to prove. You prove it directly from the definition. For greater than or equal to, so the fact that you can plug in a real number and maintain real stability has to do with a result of Hurwitz, which shows that these that real stable polynomials are closed under limits on compact sets. So essentially, the fact that you can plug in anything in the upper half plane means that you can plug in anything on the closure of the upper half plane. And so this is really nice because this says that if I can find some way to build a multivariate polynomial that I can sort of use these kinds of operations to transform it into something that I can then plug in values into, then I can show that something is real rooted that way by continually doing these operations. And there's sort of one basic real stable polynomial that everything sort of lots of times you see as the starting point, and that is that if a1 through an are positive semi-definite matrices, sum over the ai positive definite, and I think beta, B is some Hermitian symmetric matrix, then determinant of sum over I plus B is a real stable polynomial. So this matrix pencil here.
This is complicated.
No, so you essentially just factor out b, and then you use the fact that this thing has a positive square root, and you can factor that out, and it becomes a characteristic polynomial of
So maybe you should have started with characteristic polynomials.
yeah, so characteristic polynomials as, so maybe I should say that I'm thinking of characteristic polynomials as sort of being the quintessential polynomials. So for every polynomial, you can find some matrix for which that polynomial is the characteristic polynomial of that matrix. The polynomial is the characteristic polynomial of that matrix. And in many ways, this sort of extends this idea. So
Okay, so for characteristic polynomial, but it's a univariate polynomial.
this is a univariate polynomial.
So
In a minute, we'll get to hyperbolic polynomials, and those will be much more a natural extension of the idea of characteristic polynomial. But these tend to be sort of nice for their closure properties, because hyperbolic polynomials, they become a pain because you need them to be homogeneous, and you need them to sort of have other various, you need to keep track of other things. So for a lot of applications, like real stable polynomials actually are. And in fact, one of the main sort of useful results in this area is that, so here, characteristic polynomials, all univariate polynomials are characteristic polynomials. A very deep theorem of,
this is even for diagonal matrices.
yeah, you can just use, diagonal matrices. There is a result of Helton and Vinnikov, which says essentially the same thing is true for bivariate polynomials as well. So,
Sorry, you can say like, so instead of what Abby just said, that you can also use all univariate polynomials or characteristic polynomials of this form, where some AI is positive, semi-definite, or
uh,
so what is the statement for the first one?
so the characteristic polynomials, so all univariate polynomials are characteristic polynomials. And then if you want, so the question is more, okay, so
Can you write them in this form, like it's sum of, or instead of like just G A plus B, where like, well, I guess, okay, yeah, sure. If you just use diagonal, you can do that, right?
The univariate.
Just, yeah, univariate is just diagonal, right?
Yeah.
yeah, up to a shift, I guess.
Okay.
So Helton-Vinnikov says that the same thing is true for bivariate polynomials. So if P of xy is real stable, then there exist matrices and B such that, and probably I need P of 0, 0 equal to 1 is determinant of I plus x a plus y b.
A quick definitional question. So
Yeah.
a polynomial that has no root whatsoever is also stable. Like a
So-
constant stable.
Yeah, so for, yeah. We'll let them.
That's how the basic is.
Yeah. So essentially, if you're looking at a bivariate polynomial, you can write this in this determinantal form, which means that you can treat it like a determinant, essentially. So this is not true for P of x, y, z, for example.
By the way, this goes the other way. Every such
Yes, this is.
a
Yes. So this is an if and only if. These completely characterized collection of real stable polynomials. And this turns out to be very useful because if you remember this idea of substituting things in, so if you had a polynomial and you were trying to understand it, if you had a real stable polynomial, then what you can do is fix all of the coordinates except for 2. That is then a bivariate real stable polynomial. And so you can then understand how any real stable polynomial sort of varies in 2 different coordinates by writing it as this and then doing inequalities and things like that.
Yeah, so it's more useful than projecting to 1.
It is much more useful than projecting to 1, yeah.
Because you can relate coordinates to each other.
Yeah. Yeah, if you want to know like partial derivatives and things like that, it's okay. So let me finish this by giving the actual result of Gervitz. And Gervitz's result says if A is doubly stochastic, so non-negative rows sum to 1 and columns sum to 1, then permanent of A is greater than or equal to n factorial over n to the n. Which is really a, yes. But in the way that we're going to see it, it is due to Gervitz. Yeah.
Probably, yeah, it's also the proof gives much more than the original proof.
Yes, I think so.
Driver conjecture.
Yeah. OK. So given A, so here's the proof. Given A, I'm going to write a polynomial, FA.
Maybe I don't know how many people just know that this was a famous conjecture for many years, the Van der Waals conjecture, and I don't know, probably for over 50 years.
Yeah.
Yeah.
And yeah, and used these Alexandrov-Fenchel inequalities and yeah,
this number comes from just making all the entries in the matrix 1 over n.
Yeah. So let me do this polynomial, which is, so even knowing what we know right now, the idea that this could possibly be done using real stable polynomials should not be very surprising, right? Because we've seen that the original result was using Alexandrov-Fenchel, and now we're in a situation where we may believe that you don't really need the true power of what's happening in convex geometry because this is not a convex body, right? It's a matrix. So it at least seems plausible that this could be used. So Aij, Cj. So this is f of A. So I take all of the rows and dot them with this zj, and then multiply those things together. Xj. And then I'm going to look at a series of polynomials, gi of x1, xi, which is partial derivative of I plus 1 n of fa xn, setting xi plus 1 xn equals 0. So gn is fa. And I haven't taken any derivatives. And now the question is, what is G0? The permanent. And the claim is that G0, x1, xn is permanent of A. And that comes from the fact that this, taking all the partial derivatives, essentially gives you the multilinear term, so the term that has all of the variables in it. And since you can only get one variable from each row and one variable from each column, the way that those things sum up turns out to be the permanent. OK. Now, the important thing here is that for all that Gi are real stable for all I. So the fact that the first one is real stable is not too hard to prove because it's a product of linear polynomials. And certainly real stability is closed under products. And it's not hard to show that linear polynomial, that if the aij's are greater than or equal to 0, that this is a real stable polynomial. And then the fact that all of the others are real stable comes from our closure properties, right? Anytime you take a derivative of a real stable polynomial, you get another real stable polynomial. And anytime you plug in a value of 0 into a real stable polynomial, you get a real stable polynomial. So I have this sequence of real stable polynomials that starts at this thing that I understand and ends at the permanent. OK.
If you wanted to prove that the permanent is really stable,
So the permanent as a function of the variables of a matrix?
so here when you write permanent of A, sorry, yeah, this is the permanent of these numbers. It's not.
Oh, right.
Yeah, what do you mean by permanent?
So this is just a constant. So this goes back to what he was asking before.
good.
So this is sort of the yeah. OK. So let me now define a sequence S1, Sn inductively by Si is the arginf over t greater than 0 of Gi of S1 Si minus 1t.
Gi of S1 up to Si minus 1 and 2.
Yeah. So essentially, so the idea is that I'm going to start here and I'm going to sort of whittle away and get to a permanent. In order to analyze it, I'm going to go in the reverse order and say, what is the worst thing that could have possibly happened to me at each stage? Over t. It's important. So from Gervitz's lemma, this is a real-rooted polynomial as a function of t for fixed SIs. And so
Gervitz's lemma and Gervitz's inequality.
Gervitz's inequality, yeah.
It just gives a bound, right?
Yes. This says that Gi minus 1 of S1 Si minus 1, which is the derivative of this thing at 0, is greater than or equal to di minus 1 over di to the di minus 1 Gi of S1 Si over Si.
What is di?
This is the degree of Si in Gi.
It's something we could probably calculate now.
Isn't it 1?
So we'll plug them in later. But
Okay.
so it's actually interesting because in various problems you can actually change the order in which you do this iteration, induction, and actually get better bounds than the bound that he gets. If you can force these DIs to be different.
Okay. In FA, it's xj then, right?
FA
The definition, the sum is over aij times xj.
J, yes. Okay, so this gives me a string of inequalities. So permanent of A, which is G0, is greater than or equal to d1 minus 1 over d1 to the d1 minus 1 g1 of S1, which is greater than or equal to.
So this D1 is the degree of S1 in G1?
The degree of, yes, S1 in G1, which we'll mention in a second. So this is greater than or equal to product over I, di minus 1 over di, di minus 1, times Gn, which is Fa of S1 Sn. And then we get these terms on the bottom divided by and this is what Gervitz calls the capacity. Okay. So you can show, for example, that di has to be greater than or equal to I. So the original one has to be at least a degree n in some variable, and then the next one has to be at least a degree n minus 1 in some variable.
So you will go in this order of I, but it's all homogeneous, so it probably doesn't matter. So if one has such degree, then
yeah, in this case, it doesn't matter, right? And so what this says is that you get
it's greater than I.
1/2 times 2/3 squared times 3/4 cubed, so on. Everything on the bottom cancels with something on the top, but leaves one of them. So this gets you an n factorial. And the only thing on the bottom that doesn't cancel is this very last one, which is, so this actually gives you n minus 1 factorial over n to the n minus 1, which is the same as n factorial over n to the n. Times this. Right? So what I've shown is that the permanent of A has to be greater than or equal to n factorial over n to the n times whatever the minimum value of this thing is. And so now we want to show that the minimum value of this thing is at least 1.
Why is the minimum there? Why do we get a minimum? It's greater or equal?
It's at least the minimum.
Oh, sorry, because S1 will...
Yeah, that's the way we
define
chose
as
them,
a-
yeah.
Yeah, okay.
Yeah, so essentially this is, well, I think this is greater than or equal to min over x1 xn fa of x1 xn over pi over I xi.
All the non-negative guys, right?
Yeah. So now the goal is to show that this thing is always greater than or equal to 1. And again, that's not particularly hard.
So here to use the, you need to use the factor double because
This is where you use the stochastic. Yeah.
first to
Yeah.
somewhere, right?
Yes. So, let me write.
How do you get the degrees go like 1, 2, 2, 3, 3, 4?
So the di's are greater than or equal to I.
Greater than or equal to I. Okay.
So this thing is greater than or equal to 1/2,
Oh,
2/3
I see.
squared, 3/4, just iterating over.
Why are they greater than
Because you just have to sort of go back and look at the polynomial, I think. Like
You start with degree n.
you start with a degree n polynomial.
But then if I take the derivative with respect to, let's say, xn, and I restrict xn to 0, the degree of xn minus 1 is still n.
Yeah, greater or equal.
Yeah, so this, yeah, so you actually would get something bigger.
So wouldn't the degrees be always n?
So it depends on where zeros are, I think.
No, but your definition is the degree of si in gi.
Yeah, but this polynomial,
Then you fix
this thing depends on what the values of aij are.
Oh, right.
So if those are zeros some places, then it can cause it to be a lower degree.
Yes, yes.
Somehow this is suspicious because the case of equality is one where nothing is zero, and this analysis seems Gaussian, so how do you understand it?
Yeah, that is.
So we should do the half. What happens in the 2 by 2 case? So we get
So this should be, yeah, x1
plus x.
1/2.
Doesn't matter the half. Yeah. So when we
So then, yeah, it'll be, everything will be n.
but then as Mark points out, we should get a better inequality.
Right.
No, you want. That's okay. You want to prove that this is.
no, but
No, but you get
cannot get
it's
something
tight. They
better.
cannot get better than.
Why actually? How,
So if
why
everything
it
is positive, so let's say all the aij's is they're positive, then the di we know it's greater than or equal to n. It's equal to n. For all of them.
So this has degree 1 once you derive it.
Yeah. When you take the derivative of this, no, with respect
No,
to
no, with
x2.
respect to x2, but with respect to the derivative and restrict, you always have xi to the n, right? So that never goes away.
No, it gets killed.
Like with
Oh, with the
Discrete.
derivative, with the derivative. Right, okay, right, it gets
No, what's the derivative of this with respect to x2? This
To
x1. To x1.
Right, yes.
Yeah.
Yeah,
Okay,
okay.
so if all of them are positive. Sorry, the derivative is killing all the.
Yeah, the derivatives are killing higher level
Right,
things.
so it's not
Yeah.
the zeros. These are constant terms that you take.
Yeah, no, I was wrong.
Right,
yeah.
as it okay, good.
You care only about monomials.
Sorry,
Yeah, good. That's
But if there are zeros, so for instance, if you wanted to know, like for a k regular graph, what you can get a lower bound which is better because you can sort of do it in an order in which you can guarantee that these things are higher than.
yeah,
what they would be.
that's the sky that
Yeah, exactly. Okay, so let me prove that this is true. So let me look at fa of x1.
So this will equal, actually, the infimum will equal 1. I mean, the minimum will equal 1.
Will equal 1. So this is pi pi over I, aij, sj, summed over j. And by AMGM, this is greater than or equal to pi over I, pi over j, aij to the xj. And this uses the fact that the sum over I of aij is 1. Yes, sorry, xj to the ij. Now you want to sum these coefficients, so this becomes pi over j xj, and this comes from the fact that this is probably, this is sum over j, and then this uses the fact that it's sum over I. And that's it. So now that says that fa x1 xn is always greater than or equal to 1. Yeah.
It seems to me that by moving from the SIs to the mean of the entire function, if maybe the underlying problem is not very symmetric, then we may also lose something there, right?
Yes. Yes.
Like for expander.
Because
the SIs are defined like in an order-dependent way.
Yes.
Which is not really kind of interesting here. In this proof, like the values of SIs actually doesn't matter.
Right, and back to what Mark was saying, because in the sharp case, everything is the same, and so at each point the SIs are actually the minimum you could get. Okay, so any other questions on this? Yeah. How much time do we have? 45 minutes? Okay.
Yeah.
Yes. Oh, yeah.
So if you plug in something that has imaginary part greater or equal to 0, but you don't have
greater than 0, strictly greater than 0.
Greater than 0, but you don't have real coefficients anymore, right? So it's just the stability that you say in the closure.
Stability, yeah. So then real stability. So it turns out that
real stability is just you plug in reals, then.
No, real stability is the coefficient.
Real stability is the coefficients are
Yeah,
real.
but then he has property 3 that like. The property 3 that you named, like.
Oh yes, that's right. Right. So, okay. So this actually does preserve stability.
Stability, but then
Yes.
here you only need the real stability because you plug in reals only.
Because I'm plugging in reals only.
Okay.
Yes. But actually, plugging in reals is the hardest part of that
Of that proof. So.
of showing that
Right, because if it's already stable, then.
if it's already stable and you plug in something in the upper half plane, that's essentially like.
So we might as well just say okay.
Yeah.
T is equal to.
Other questions? Okay, so the other thing I wanted to mention regarding real stable polynomials is that a lot of work has been, especially in computer science, has been done regarding what are called strongly Rayleigh distributions. So these are distributions which have so these are distributions on 0, 1 to the n. Rayleigh, R-A-Y-L-E-I-G-H. Yes. And these are these are distributions where if you write out G mu is sum over s, probability of s, x to the s, this sort of probability generating function. So
So we should understand the PS as the probability of the vector.
yes, sorry. Probability of picking this set times all of the variables associated to that set is called strongly Rayleigh if strongly Rayleigh if G mu is real stable. So one particularly well-used strongly Rayleigh distribution is the spanning tree distribution. So if you put weights W of E on the edges, and then you define P of T is pi over E and T W of E.
That's for a tree.
For, yes, over trees. Subtrees, and then I want to call this lambda. Then you can have a distribution which is a normalized version of this. So lambda of t over sum over all t lambda of t.
So that's really, that's P of G or something?
P, yeah, P of t.
That's a
Yeah.
normalized, yeah.
This is a normal. This turns it into a probability distribution. And the fact that this is a strongly Rayleigh distribution comes from the matrix tree theorem, essentially. It tells you that you can write, that if you look at essentially the characteristic polynomial, although you have to do a sort of a multivariate characteristic polynomial, if you multiply that out, all the things that are not trees become 0, and all the things that are trees stay and give you a weight of this product of the WEs. And so this is a strongly Rayleigh distribution. And the reason that strongly Rayleigh distributions are nice is because for one, they have what's called negative associativity.
So, okay, the distribution is over some of the edges, so that's really the...
Yes.
In general, I mean, when you write G mu, it's really the variables are the edge names.
Yeah, it's just yeah, exactly. So what's nice about strongly Rayleigh distributions? Well, first of all, so conditioning a strongly Rayleigh distribution gives you a strongly Rayleigh distribution. So I'm told this is actually one of the most important things that they're. So if you wanted to know the probability, for instance, instead of taking probability of t, you wanted to know things like the probability of t given E1 is in t. So I am told, most sort of probability collections of probability distributions that you have, when you condition on things, like you don't get out something else in that collection. But here, conditioning is essentially like either plugging in a 1 into this polynomial or a 0 into this polynomial, in which case you're just turning a real stable polynomial into another real stable polynomial. So this is closed under conditioning. and it is what is called negatively associated.
Under this kind of condition, I mean, you could be another kind of condition.
Yeah, you could do any kind of, yeah. No, it's closed under essentially any conditioning that you want to do. I mean, the conditioning is either like oh, I see what you're saying. Yeah, no, it's not going to be over like things like x1 plus x2 equals 0 or something like that. No, yeah, just conditioning over setting variables. And in particular, negative association implies like various Chernoff bounds. So these things sort of have all of the large deviation inequalities that you want, and so I just wanted to mention that. Now, and this actually, so this idea is essentially has what's gone into all of this work of Ove-Scaron that improves the approximation algorithm for traveling salesmen. Yeah.
There's another work that's of Distributional that just uses the van der Waals conjecture, also for the permanent bound, for the traveling travel.
For the travel. Oh, I didn't realize that.
Yeah. Doesn't use this.
OK, so the other type of polynomial, the other sort of area that is useful in this sort of study is regarding what are called hyperbolic polynomials.
So you are switching topics.
I'm switching topics.
Just to say that it's just
This is the end of real stability. Yeah. Now I'm moving on to hyperbolic polynomials. And this is really sort of one of those situations where people were doing essentially the same thing, but in sort of different ways at the same time without really knowing it. So hyperbolic polynomials were actually introduced in the partial differential equations community for whatever reason. And sometimes they're easier to deal with, and they have sort of easier properties to deal with than real stable polynomials. Other times, real stable polynomials are easier to deal with. But there's a way sort of to go back and forth between the two of them. I mean, I won't say here, but essentially anything that you can say about a hyperbolic polynomial, you can say something almost equivalent about a real stable polynomial. Anything you can say about a real stable polynomial, you can say something almost equivalent about a hyperbolic polynomial. So a hyperbolic polynomial is a homogeneous polynomial, multivariate. So here I have to say a hyperbolic polynomial is multivariate homogeneous polynomial is hyperbolic in direction E if P of x minus TE is real rooted for all x. So here is where this picture sort of starts to make more sense. So what ends up happening, so now you have a homogeneous polynomial. So all of the sort of lobes have to go through 0. So now,
So that's the univariate polynomial.
this is, yes, univariate.
Univariate polynomial.
This is a univariate in T. And then you have essentially something that looks like this. Something that looks like this.
These are the zeros of the polynomial.
These are the zeros of the polynomial. And what does it mean? So each of these sort of has like this, every hyperbolic polynomial is hyperbolic in two different directions. And essentially what this hyperbolic direction is just telling you which lobe you're going in. So like for a while I thought that maybe this sort of meant something, but it really is just sort of telling you what lobe you're talking about. And one of the main theorems in...
If this is a polynomial, in which direction is it hyperbolic?
So you could say it's hyperbolic in this direction, in which case this would be your hyperbolicity cone. Or you could say it's hyperbolic in this direction, and then you're talking about this hyperbolicity cone. Or you could just say that it's hyperbolic, in which case I think people sort of assume that you mean whatever the positive cone is. But sort of the main result that made these hyperbolic polynomials interesting is a result due to guarding.
Maybe it's just my memory. I thought it needs to be positive, not just go in some direction where it will remain positive.
So that's going to be the definition of your hyperbolicity cone.
Oh, I see.
Yeah. So okay. So the point is that guarding showed that the collection of x for which p of x minus te has only negative roots is connected and convex. So essentially this guy right here what does it mean, this p of x minus te? It means that if you sort of drew a line in this direction, you would have to cross all of the different lobes. And the claim is that this lobe, which is sort of above all of the roots of anytime you're sort of above all of the singularities and below all the singularities, you're living in a convex cone. And so this sort of brings about so let me start by saying, let me give some examples of hyperbolic polynomials. Maybe easier. So, example 1 is the multilinear polynomial x1 through xn. And then your sort of zero things are actually just the faces of the orphans. And this is hyperbolic in the direction 1, 1. And the hyperbolicity cone yeah, that's true. And yeah, this is sort of a degenerate sort of case. The hyperbolicity cone is the positive orphan. A second one is what's called, well, let's see, this is x n plus 1 squared minus sum over I xi squared is hyperbolic in the direction 0, 0, 1. And its hyperbolicity cone is a set of x such that xn plus 1 is greater than or equal to 0. Is this thing. This is called a Lorentz cone. And
This is like a sphere, right?
uh,
Half of a sphere.
this,
Sorry, for every xn plus 1. No, the cone is. I mean,
the cone, so this should be,
This polynomial, I mean, it's zeros are spheres, right?
uh,
This x plus xn plus 1.
then everything
The
will be a
radius
sphere,
of
yeah.
the sphere, right?
Yeah. So that's the cone that you would do quadratic programming on.
Okay.
And then the last one is P of x, where this is n plus 1, choose 2 variables, is determinant of x. So it's a variable for the diagonal, each of the ones in the diagonal, and a variable for each of the things in the upper coordinate, and then
Symmetric.
is a symmetric matrix. Yeah. Symmetric. And this is hyperbolic in the direction the identity, and its hyperbolicity cone is the set of positive semi-definite matrices.
So in these examples, the properties are easy to just figure out and just by the definition. That they are hyperbolic in this direction and that this is a cone.
Yeah, yeah. Yes. And so in many ways, so this sort of turns into, this is essentially a characteristic polynomial. And in many ways, there's a sort of correspondence between hyperbolic polynomials and characteristic polynomials. So in particular, so remember our polynomials are P of x plus te. So you have a map from x, which is your input, to lambda, so the roots of, let me call this lambda, so the roots of P of x plus te. And this satisfies that lambda j of sx plus te is s lambda j of x plus t for s greater than or equal to 0, s lambda and these will be ordered. And P of x is,
What are you writing down? The s's are the roots, but there is a parameter s there in front of it.
yeah, let me not do that. Lambda 1. And So this sort of tells you sort of what, imagine this was determinant and X was a matrix and E was the identity. Then if you wanted to know the eigenvalues of S times X plus some multiple of the identity, it would be exactly adding these T's and multiplying by S, unless S was negative, in which case it would reverse the order and then add these T's. And on the other hand, it behaves sort of like a real-rooted polynomial in that you can factor it in a way that makes it obvious that this is a sort of as a function of the zeros.
So wait, this is for any hyperbolic polynomial, or this is just for the
This is for any hyperbolic polynomial.
where the determinant comes up?
Yeah, I think of them as the hyperbolic polynomials are sort of, I see as an extension of linear algebra in many ways, characteristic polynomials. And another reason that that's true is that hyperbolic polynomials tend to have the same sorts of convexity properties that matrices have. So there's this theorem of Davis on Hermitian matrices, which says that if F is a unitarily invariant matrix function on Hermitian matrices, so it means that F of Q star MQ equals F of M for all unitary Q. What it really means is that it only depends on the eigenvalues of M. So if you have some function which only depends on the eigenvalues of M, then F is convex on all the Hermitian matrices if and only if F is convex on diagonal matrices. So essentially, if F is a convex function, period, then F of lambda of X is a convex function. So this is like saying it says F convex implies F of lambda of X is convex.
Well, the other direction is a non-trivial one. Because what does the left-hand side mean if it's a function of matrices? I mean, clearly, diagonal matrices are Hermitian. So in this if and only if, the fact that they are
I mean, so this is saying that F is a convex function, right? Just plugging in numbers.
yeah.
And so F being convex on the diagonal implies that F is convex as a function of Hermitian matrices.
Right, so that should be the non-trivial direction.
Right.
Right.
Is that not what I?
Yeah, I don't know what. So you mean F convex as when we think of it as a function of n number?
Yes.
Yeah,
F as a function of.
Oh, yeah, because it's written in the.
Sorry.
Okay.
And a very useful.
So, by the way, convex here is convex in every variable. Or convex, sorry, it's not convex.
Just yeah. and a very useful theorem of Blaschke, Euler, Lewis, Sendov says that the same thing is true for hyperbolic polynomials. So if f is a convex function, then f of, we call this lambda p, is convex.
And this is a strict generalization because you could take this characteristic polynomial
Right.
and the characteristic polynomial will be hyperbolic. So it does not depend on which direction it goes. The definition of lambda p depends on the direction
Yes.
in which it is hyperbolic. So can you show any application of this?
So depends on what you mean by useful application.
Any use? No, any place is used, not that.
So there is this characterization of what it means to add two Hermitian matrices together, like what the eigenvalues have to satisfy.
Yeah, it's a big.
Yeah, so something very similar to that is implied by this. So it gives you a collection of inequalities that tells you, if you take
All the inequalities that must be satisfied.
have to be satisfied by hyperbolic polynomials as well.
So there is a similar theorem. So
Yeah.
this has to be to do with the saturation of.
The proof that this is just. I think this is from the 70s, and it just is what it is. But the fact that you can characterize so it was sort of always known that all of these matrix inequalities were true. The hard part of the proof was showing that they were actually sufficient for characterizing. So this is true is not anywhere on the level of what Tau and Knudsen did, whatever.
So there is an old problem that was recently solved. I don't know exactly within the last decade. What can you say about what inequality should be satisfied by the eigenvalues of the sum of two, let's say, Hermitian matrices whose eigenvalues, so you have the two eigenvalue vectors of the two matrices. And what can you say about this?
Yeah.
So there are obvious ones that you could think about, and there are many non-obvious ones, and yes, this was characterized. So similar question should be asked. So that's in this sense you meant this a generalization.
This is just a generalization of those inequalities.
So another couple of n numbers that
Yeah.
behave like eigenvalues.
Okay, so why are computer scientists maybe interested in this? Well, the point of having the hyperbolic, do I still have a picture over here? I don't. So if you remember this hyperbolicity cone, is convex, and so you can optimize functions over it. But more is true if p of x is a hyperbolic.
This is not obvious in that one has to have a good representation of this, like a separation oracle for this. Is this clear that we have a separation oracle for this convex body? Otherwise, you cannot optimize over.
Well, p of x is hyperbolic implies that minus log of p of x is a concordant barrier function, which means you can do interior point methods.
I see. So it's not the ellipsoid method that's used. It's not the fact is that when you read convex and you say optimization is doable, you need some.
I think you can use the ellipsoid method to show that this is a polynomial time algorithm, but I think that
But that's not interior point method is completely different than ellipsoid method. It's very different.
Yeah, okay, so I don't know what the... So I think you can use, so you certainly have, right, so you certainly have, like you said, an oracle that tells you whether or not you're in the convex cone or not.
Yeah.
Yes.
This, why?
So you can write the hyperbolicity cone as, so you can write P of x plus TE as, so write this as a polynomial in T. This is sum over K, sum AK of x, T to the K. And you're in the hyperbolicity cone if and only if all of these AK of x are greater than 0. So in hyperbolicity cone, if and only if all
Yeah, so it's not clear how to compute them.
Yeah, and in particular, it's not even clear, saying P of x is hyperbolic doesn't really help you either, because if you gave me, the determinant, which is the hyperbolic polynomial, but you gave it to me not as determinant, but you gave it to me as a sum of, sigma, minus 1 to the sigma times, all of these terms, then even evaluating that polynomial becomes very hard. And you can't do it.
So this characterization, which is nice, it's not an effective way of providing. It does not give automatically a separation.
It does not give you that's definitely not
To
true.
check this, to evaluate one a sub k may be very difficult.
But you can have a circuit for P.
Even if you have a circuit.
Oh, you can interpolate,
Suppose
right?
what?
You can oh no, you have to do it for all x's in the real, right? Oh, I see. Okay. Yes.
No, you want to know which x's.
Right,
The
you want-
polycity cone is those x's for which this is satisfied.
Right. Okay.
Yes. So one of the big questions in this area is, so in particular, so linear programming is a version of hyperbolic programming. You're doing linear programming over this x1 through xn. Versions of quadratic programming are hyperbolic programs where you're doing your optimization over this Lorentz cone. Semi-definite programming is a type of hyperbolic program where you are optimizing over the hyperbolicity cone of that determinant polynomial. And one of the big questions in this area is there anything else?
So you said that semi-definite programming is a special case of hyperbolic?
Is a quote-unquote special case of hyperbolic programming. So
Clear what happens when you add linear constraints to this kind of.
that's true. Yeah, I'm not sure.
You can do eigenvalues, but that's obvious.
But I think you can do this sort of thing where you can encode some of these linear constraints in the polynomial itself, I think.
And it remains hyperbolic.
I think so, yeah. Like a product of, yeah, I think so. So there is what is called a semi-definite representation of a hyperbolic polynomial, well, let's say a hyperbolicity cone, is a representation of the form S, call this S.
So now you're going the other direction. Now you're going in the other direction, you're representing the hyperbolic.
So this is the question, is whether hyperbolic polynomials, whether the hyperbolicity cones really give you anything new, or whether you can essentially optimize over them by doing extensions of semi-definite programming. So S is a collection of X such that Y are in S, where S is the collection of F0 plus and the Fi's and the GJ's, say positive semi-definite. So this is essentially some projection of some larger semi-definite programming, semi-definite cone to a collection of variables. And it is unknown, so there do not exist any known hyperbolic programs which cannot be formed in this way. In particular, a very nice result of Perillo and Saunderson shows that sort of the first obvious thing that you would try, although it's certainly not an obvious proof, is that, so Perillo, Saunderson, is that the derivative cone of, so all derivative cones of the semi-definite programming cone are semi-definite, or have semi-definite representations.
The number of y variables is polynomial in the number of x variables.
Yes. Yes, it's buildable with a polynomial number of new variables. So you can optimize over the SDB cone, you can optimize over the cones which are derivatives of that polynomial simply by doing semi-definite programming. Although it is unclear, almost in all cases, whether or not actually doing that the semi-definite representation actually helps you in any way, because you're adding enough variables in many cases that it runs much slower than an actual hyperbolic program would. There was something else I wanted to say. So the other thing is that hyperbolicity cones tend to be much less nice than semi-definite cones. So for example, semi-definite cones are self-dual. Hyperbolicity cones are certainly not self-dual, and in fact, the dual of the hyperbolicity cone is not necessarily a hyperbolicity cone. So it's not even closed under being a hyperbolicity cone. So that sort of handcuffs you in sort of the primal dual methods that you can possibly come up with. And this is also, I think, I mean, it's sort of one of those weird areas where like actual theoretical mathematicians really want to know these things too. So this is a big open question in real algebraic geometry as well, whether or not hyperbolic polynomials give you anything new that semi-definite other than essentially the determinant polynomial. Questions?
Questions?
That's all I was going to say. If,
So you know any place where people are using hyperbolic programming instead of or what kind of programming people would be using hyperbolic programming as opposed to?
So I think Levent Tunzel is sort of the person who is Tunzel. He's at Waterloo. He is sort of the one person I know who is like actively working on these things. So Jim Renegar was doing them, like he sort of was doing them originally, and his hope was sort of that the idea would be that the derivative cones would be relaxations. You could take an SDP and then you could take relaxations of it by just taking the derivative, and then you could say something about, I don't know, some. But then that didn't really pan out, I guess, into what he had hoped. But then when Pablo showed that those derivative cones are semi-definite representable, Levent has some software that he can use to solve those derivative cones in like some absurdly small amount of time compared to what the semi-definite program takes. So even though it's unclear whether or not there are...
When people do hyperbolic programming, they use this?
They use that actual, yes.
Just the interior point method.
They use the interior point method, yeah. And they use like the long steps, and so... and I think in the convex optimization community, like it's sort of a nice halfway point between semi-definite programming and convex programming. So like it has some structure that you can work with, and so it tells you sort of a lot about So I think he uses that to understand like more general convex programming than semi-definite programming, but I don't know any like actual. So you could make the claim that our solution of Caddis and Singer was solving a hyperbolic program by starting with a semi-definite program, and then that the solution to, and then transforming your cone by hitting it with various operators, and then bounding where the optimal solution, or showing that that you can move to a new place, which is still a valid solution or whatever. Except that you're actually probably solving that. You're solving it in the dual hyperbolic cone, so it's not really.
Even a simpler thing like the falsifier of Spielmann's Sebastian can be thought of as in this way, in just some sense.
So their sparsifier, I think you can just do. I mean, that's just like greedy, essentially. I think it's.
Yeah, but the bound. Okay.
Yeah, right. So the bound, so the bound that you get, you can think of it as taking a semi-definite program that and then massaging it into something else, and then maintaining feasibility along the way, and showing that whatever. And in fact, it uses the same. I mean, the barrier function that are used in all of these things is the same barrier function. So it's the.
That's what I meant. The
Yeah.
function.
So that's probably, I mean, Levent seemed very excited when he saw our result, because he sort of thought that was the most useful thing that he's seen related to hyperbolic programming. But certainly I think that people are interested in these semi-definite representations. I mean, I know that there's at least 3 communities working on them. There's the control theorists are very interested in these things as well.
More questions? Okay, thanks a lot.
Thank you.